Hello everyone. In our today's session, we'll conduct experiment 1 with respect to the verification of sampling theorem. So myself Srishan R, Assistant Professor, Department of Electrical and Electronics Engineering, ETME College of Engineering, Mysore. So with respect to the contents, we'll speak with respect to the initial discussion on why this experiment is required, followed by which I'll talk about the applications, followed by the program with respect to the execution using the software tool. So when we talk about sampling, let us understand that this is a continuous signal and this is a discrete signal in very fundamental representative form. Now, why we need to study this experiment? So a signal has three different properties like voltage, what we call it as an amplitude, frequency and phase. So when we talk about representing an analog signal that is continuous in nature in time and difference in voltage level for different periods of signals, so the drawback when we talk in terms of this particular signal is that it keeps on changing with its period of signal, that is the amplitude keeps on changing. So if it has to be stored in digital form, how are we going to do that? So here we have a representation of continuous signal, and what you are seeing at the points, these are discrete intervals of points being represented. So if I have to store a continuous signal, let's say for example in physical world we have speech signal, we have audio signal, we view somebody, so it is basically captured in our visual eyes, and then it is stored in your our processing system, that is basically our brain. But in physical signal, if we have anything in analog form that is picked in through a sensor, it has to be stored digitally. So a continuous signal has to be converted into a digital form, and that data has to be stored in, let's say, a pen drive, a hard disk, or it can be a memory, basically a RAM and ROM, what we call it. So this can be done using a technique called as sampling. So here we can see an analog signal, a sampled pulse train signal, and a digital signal which is retrieved back later on. So continuous signal is converted to digital signal using a A to D converter, that is analog to digital converter. The converted digital signal is stored, and once the digital signal is stored, let's say like I gave an example of different platforms, that is a floppy disk, pen drive, hard disk, or a cloud, then it has to be retrieved back to its original form. So again a digital to analog converter is used and it is retrieved back to its original form. So when we talk about sampling, it is basically reduction of continuous time signal to discrete time signal. So when converting from analog signal to discrete form, we use sampling technique. So it is very important that we understand what is the sampling technique and what are the reasons that basically that is the distortions while we are sampling a signal from continuous to discrete form, and again retrieving it back from digital to analog form. So the scientist Nyquist basically proposed the sampling theorem. So what does the sampling theorem say? That is, if I have a sampling signal, or in very simple terms, sampling signal frequency, it should be double the input signal's highest frequency component to get a distortionless output signal. So here we can basically see the sampling frequency should be greater than or equal to the maximum input signal frequency that we have it in our signal. So what are the applications that we can have for sampling? So basically you have sound quality in music recordings, that we can use it as an application, speech recognition system, pattern recognition system, modulation and demodulation systems, data evaluation systems, radar and radio navigation systems, digital watermarking, biometric identification, surveillance systems. There are numerous applications that we are talking here, but anything in real world, if you are converting from analog to digital, then the applications can be innumerous. So continuing with respect to the experiment, let us start off what is that we are going to learn here. So the objective is to learn the physical interpretation of sampling theorem, and followed by which we'll understand this both in time and frequency domains. So the software that we are going to use for this is Octave 5.0. So basically this is the free version of software that we are utilizing. You can also perform or execute this program even in MATLAB, that is Matrix Laboratory as well. But since we are talking with respect to freeware, we are using Octave here. So the program goes like this. So here we are using CLC. CLC is basically clear screen. So if you open up a software, you will be having command window where we'll be basically using this command to clear the cache. So followed by which I'm using the supply frequency right now here as 50 Hz. No hard and fast rule, you can use different frequency. So I'm using the time period here as t is equal to 0 to 0.001 is to 0.04. So I have the time period from 0 to 0.04. So here this in the middle, what you're seeing, that is after this is to sign, this is indicating the sampling rate. So we know the equation for sine is 2 pi, sine of 2 pi ft. So to get a continuous signal, we have sine of 2 pi ft. So this I'm indicating to a representative signal over here. So basically this we are representing to the Y signal. So Y signal is basically carrying that output signal over here. So if I have to plot this, I'll be using the plot command, that is with respect to time period t and the continuous signal y, which I'm documenting over here. So t and y, that is with respect to the amplitude. So if I have to plot this, I need to have a lot of subplots in a single window. So if I have let's say a big image and I want to plot a sub image, then I'll be using this subplot command. So here I have 3 rows, 3 columns, and the first image in this I'm considering over here. So the image looks something like this. So here I'm showing only one plot right now. At the last I'll be showing you the complete plot representation. So here we can see the time period being 0 to 0.04, 0 to 0.04 and 0.01, or you can also have it at any intervals of sampling that we basically desire for. Need not have to be only, and you can basically check out how it is performing as well. So now I have a continuous input signal. Now I want to sample it so that I can retrieve it back or reconstruct it back to its original form after conversion from A to D and again back from D to A. So in the first case, I'll use the sampling frequency equal to supply frequency. So Fs is equal to Fm. So basically my sampling frequency I'll be considering here as 50, that is equal to the supply frequency, which is 50, which I had considered previously. So here my time period length I'll be considering as 0 is to 1. Next, my output I'll be plotting this as sine of 2 pi f. This time you can basically check out it's a discrete signal that we are trying to understand over here. So it is n divided by fs1. Now what is this n by fs1? So t is equal to 1 by f or f is equal to 1 by t. So in place of this t is equal to 1 by f, I am plotting this as n. N here represents the time period. So I have considered here as 1. So 1 divided by 50. So whatever that 1 divided by 50 is there, that will be indicating my time period. So basically here this will be plotting in terms of our subplot, that is 3, 3, 2. So I have already got the input signal. Now I'll be plotting my graph in the second half and I'll be using my stem command. Stem command is basically conversion of analog signal to discrete form. So if you have a continuous signal, which we already came across in a previous slide, that will be represented in the discrete form. So here n represents for discrete representation, t is used for continuous representation. So n is our time period, y1 is what we have got with respect to the equation. So here the hold on command is used for conversion of analog to digital. So if you are not using this hold on command, the conversion process basically this may be delineated and you may not get the requisite output. So again, to represent this back in our analog form, I'll be using the plot command, that is plot of n, y1, and I'll subplot this in 3, 3, 3. So this 3, 3, 3 basically indicates your continuous and discrete representation. So here this is your 3 column, 3 rows and third image. So basically if I have to tell, this representation over here is the stem representation, stem n, y1. So this we have got it over here, and again plot of n, y1 is represented over here. But here you can basically see, since the sampling frequency is equal to supply frequency, neither I am getting both of the representation is absolutely not correctly sampled, and because of which you can see you are not getting or retrieving back the original continuous signal representation. So I'll go for the next case and check out what is going to happen. So I'll be sampling the frequency greater than twice the supply frequency. So once I do this, let's say I pick up the sampling frequency as 500. So if sampling frequency is 500 greater than equal to 2 times the supply frequency, 2 times the supply means 2 into 50, that is 100. So 500 obviously is greater than twice the supply frequency, that is 100. So I'll be enhancing the time period to 20 now. Need not have to be 20 only, you can consider 30 or 40, that is your choice altogether. So here, now my representation I'll be changing it to 2. Previously you can see FS1 I had considered. Now I'm changing it to 2 over here because redundancy in the program will lead to wrong data representation. So that is the reason why I've changed the representation to 2 over here. So sine of 2 pi f, now this becomes n divided by fs2, n is 20 over here. So n 20 divided by 500, that represents my sampling rate right now. So I'll plot this in as 3, 3, 4, that is 3 column, 3 rows and the fourth image. So I'll use the stem command for representation from continuous to discrete. So n is 0 to 20 time period. Y2 is my new equation that I've got out, and continuous to discrete representation, to actually achieve it I'll be using the hold on command. Finally, if I have to plot it back to continuous representation, I'll be using the plot of n y2 command, and finally this will be represented as 3, 3, 5. That is the new image. So here we can basically see 0 to 20 being the time period. So this is your stem function representation, that is continuous to discrete, and again to represent this back in original continuous form, that is n y2, we have used the plot command. So here we can basically see we have got the original signal that is retrieved back in correct representation as per the theorem, that is Nyquist condition. So what you are seeing over here, that is the sampling rate, that is 20 divided by 500. So whatever value that you are going to get, that is sampled at regular intervals of time period. So please ensure that this particular signal is very important, that is sampling. If it is not the case, then probably your output signal will be delineated or what you are reconstructing back. So 0.04 is the sampling rate, that is 20 divided by 500. So 0.04, 0.04, 0.04, it will be sampling up to 20 time period. Let me check out for one more case now. I'll consider the sampling frequency, which is to be very, very much greater than the supply frequency. Or here in this case, it should be, let me just correct it. So we will be using this very much greater than the supply frequency. It's not just twice. So so let us consider 1000 now. So we are considering this as fs3 1000 as against 500. So let me enhance the period to 40 time period. My equation now will be y3 because already we have used 1 and 2 representation. Now it is n divided by fs3, n is 40 divided by fs3 1000. So we will be getting the time sampling period. Now I'll plot this using these three commands. 3, 3, 6 represents third column, third row and sixth image. I'll be using stem function for continuous to discrete representation. I'll be holding on that command during the process of conversion. Now once this is done, I'll plot this back in continuous form and see how it basically looks like. So this is the sampling rate, what you are basically getting after dividing 40 by 1000. So 40 by 1000, whatever value you get, that will be sampled at interval of period up till 40. So once you retrieve it back, you are getting the signal over here. So this is called oversampling condition. So basically at the end, whatever you are getting, this is a pictorial representation. So 1, 2, 3, 3 columns, 1, 2, 3, 3 rows. So this is 3, 3, 1, 3, 3, 2, 3, 3, 3, 4, 5, 6 and 7. So this is your input signal. These two images are for your undersampling condition. These two images are for your Nyquist condition, and these two images are for your oversampling condition. So at the end of the case, if I show the result, we have executed for undersampling for fs is equal to f, that is 50 Hz. Next Nyquist condition, fs greater than equal to twice the supply frequency, that is for 500 Hz, and oversampling, that is for 1000 Hz. 1000 Hz greater than very much greater, that is with respect to supply frequency, which was 50 Hz. So if I have to execute this with respect to your software, so let me just click on Octave 5.1 over here, that is GUI. So when the software opens up, you'll be getting two windows. This is your command window and this is your editor window. So command window is where you check out the output, editor window is where you type here. So let me just copy the program. So I've already copied this in one Word file. In your case, you have to type it. So I'll just come back and I'll paste it in the editor window. So once this is done, I have to save the file. I have to save the file. Say I'll let's say go to desktop and I'll create a new folder by my name and I'll save it as experiment1. And very important, when I was saving, if you had observed carefully, I'll just go back once again. Experiment.m. .m represents .matrix. So here in the file section, when we are saving, you see basically it is .m. So if this is selected as all files, you should be giving it as .m. But if you are scrolling down and if it is saved as .octave files, you can just save it as experiment1. By default, it will save under the file extension as .m. I hope I'm clear with respect to this. So now we'll execute and check how exactly the output looks like. For this, there is a button down here called as save file and run. Already we have saved it. I'll directly click on this, and here it is asking whether I should change the directory or add directory to load path. You have to click on add directory to load path, indicating that you are saving the file inside the folder Sri Shayana, which I had created in the desktop. So I'll add file to the desktop, and here I'll come to the program. So there's a syntax error that it is asking. Let's say I'll just come back. There is a error somewhere in the program. So I think, okay, so let me come back. Here you can see there is a line called as program. This is not part of the program, so I have to comment it. So I'll just use the percentage symbol to comment this particular program. Now I should be able to execute this. I'll click on the run button once again, and we'll be getting the plot here like this. So this is a continuous signal. This is for undersampling condition, Nyquist condition, and finally oversampling condition. So this is all with respect to experiment 1. Thank you.